We organize the talks into 4 sessions per day. So 1 hour, 20 minutes per session. We have one coffee in the afternoon, one in the evening, and we split it up by lunch in the afternoon, which is 1 hour 30. The talks are 15 minutes plus 5 minutes of questions. Keep it tight, we want to stay on schedule. The chair is going to remind you when you have 3 minutes left, but it's a bit tricky to send reminders over Zoom, so it's good if you also keep timers on yourselves to keep track of your time. For questions, like I said, ask questions after the talk. It's better if you don't interrupt during the talk. Raise your hands. There is a button at the bottom of the Zoom window under reactions. You can raise your hands, and then the chair will point you out to ask a question. We enthusiastically encourage questions, especially from students and young researchers, and I kind of prefer if the chairs give priority to the young people. Remember, no question is too stupid. At least that's my view. So feel free always to ask questions. We have a code of conduct. Let's see. I'm going to just share the screen quickly. We have a code of conduct written on our webpage that you can see, and I recommend you familiarize yourselves with it. But to summarize, the code of conduct says just be nice to each other. That has always been the case in previous Ramses users meetings, so I have no doubt that you are going to continue to do that. What else? During the breaks, we encourage people to use the wonder.me virtual room just to have discussions about whatever, can be related to Ramses or fermented shark or anything really. We prefer not to put the link to that on the webpage, but I have sent emails to everyone with the links to the link to the wonder.me page. And it's also on Slack. I hope everyone has already been invited to the Team Ramses Slack, where there is a RAM21 channel, and the link to the wonder.me page is there, along with the links to all the Zoom sessions for the meeting. If you have not been invited to the Slack, just give me a ping, send me an email, and I will invite you to it. We recommend using Slack for any kinds of discussions. Also, there is a channel there for technical issues, if you have problems connecting or anything like that. And we will keep an eye on it and follow up if there is anything. And of course, not just during the meeting, but after the meeting, the Team Ramses Slack is actually very useful to post problems that you have with Ramses, to ask questions. You can have lively discussions there. It's been very useful for me in the past, and I recommend that you keep using it after the meeting. Now for the hackathon, so it's become kind of a tradition that we have done hackathons in Ramses users meetings. Because this is an online meeting, it's not very convenient to do that in a similar way that's been done before. So we are not going to officially support a hackathon in this Ramses users meeting, but we have set up a Google Doc for people that are interested in organizing their own kind of hackathon sessions. So, after the meeting in the latter half of this week, you can access this Google Doc, and then it's nice if you have some projects that you collaborate on as a result of this meeting, some hackathon project, that you put a description of it there just to record, and we can, yeah, I mean, it's good to keep track of the progress that is made during or because of the meeting. There is a link to this Google Doc on Slack, and I'm not sure if it was in the emails I circulated, but it is on Slack. Okay, so let me just finish by saying that I look very much forward to seeing all your talks in the next 3 days and see what you've been up to in the last 2 years now. So now I give control to Adrianne, who is the chair in this session. The session starts in a minute and a half or so. So we have about a minute silence and then we start. Thank you, everyone.
Thank you, Yoki. Thank you, the organizers. This is great. It's so exciting. We're going to have one of these meetings again. Can I invite Warren to put up his slides? And I guess, Yoki, you want us to wait till 9:30, right? We'll take, okay. So as Yoki said, I'll be giving a 3-minute warning before the end of the talk. So I'll try to wave 3 fingers. But if you don't see me, then I'll also speak up.
Yeah, sure. I've got a timer as well. You can hear me all right, correct?
Yes, perfect.
Awesome.
Okay, here we go. So to kick this off, we've got Warren Massoneau, who's going to talk about super Eddington and a collapsing dark matter halo at high redshift.
Thanks for the introduction. So I'm Warren Massoneau, a third-year PhD student at IAP in France. I'm working with Martha Lanteri, Johan Dubois, and Ricarda Beckmann, and as Adrianne said, on the topic of super Eddington accretion. So we're interested in Ramses to understand how massive black holes at high redshift have grown so quickly. So that's why we try to study this super Eddington accretion. So to start things off, I'm going to introduce you to what is the Eddington limit. Here you see a black hole that is surrounded by a gas shell. And as the gas falls in towards the black hole accretes it. And as the accretion rate goes up, so does the feedback luminosity, which increases basically up until the point where the photon pressure forces are actually greater than gravity, which basically pushes the rest of the gas shell away, and therefore accretion stops. So when we say that a body radiates at the Eddington luminosity or accretes at the Eddington rate, so basically is at the Eddington limit, it means that there's an equilibrium between the radiative pressure forces and gravity. This limit has actually been known for exactly 100 years now. However, several analytical models as well as numerical simulations actually showed that the super Eddington regime could be possible and potentially explain the very rapid growth of black holes. So to measure how efficiently a black hole is growing, we define what's called the Eddington fraction as the ratio between the bolometric and Eddington luminosities. And usually when we are below the Eddington limit, the factor of proportionality between the luminosity side and accretion rate side of this equation is equal to 1. However, that's not really the case when we are above the limits. When the Eddington fraction is greater than 1, we find that the super Eddington regime is actually radiatively inefficient. This is due to what's called the photon trapping effect, where basically photons are just trapped within the inflow of matter and cannot be radiated away from the disk. So this effect has actually been seen by several studies, as you can see here. However, there's a little bit of discrepancy regarding how effective the photon trapping effect is, as you can see by the different results that you get. Another difference with the sub-Eddington regimes is the feedback and outflows, which are in the forms of thermal winds and relativistic jets, basically. So these teams that I just talked about have actually studied super Eddington near the black hole, where their resolution could go down to the Schwarzschild radius. However, what we are interested in is what happens at larger scales, so from parsec to kiloparsec scales, where the gas supply is located at. And one of the main questions that we ask ourselves is whether or not the super Eddington accretion can actually proceed long enough to have an impact on black holes' growth. So in order to actually look at this, we do this in an idealized setup, which is a collapsing dark matter halo. So the halo is about 50 kiloparsec wide, has a mass of 10 to the 11 solar masses. And as it collapses, as you can see on your screen right now, if the movie plays properly, a galaxy starts to form. And after several star formation and supernova events, we add a 10 to the 6 solar masses black hole that is symbolized by this little circle. And the environment of this galaxy is such that super Eddington accretion is actually possible because the gas is very dense and quite cold. And that's actually visible when we have a look at this in the black hole mass evolution, where basically we did several tests in order to see how the black holes was growing. And in the case without any AGN feedback, allowing for the black hole to accrete above the limit as soon as it can, we found that the black hole's growth was reaching within just 100 million years more than 100 times its initial mass. And to give you an idea of how fast that was, I've plotted here in red, the dashed red lines, the actual Eddington limit of this black hole. So clearly the growth is enormous when we go beyond the Eddington limit. However, obviously in this run, I did not include AGN feedback. So what happens when we do so? So I will talk about today a comparison between this run with super Eddington in orange and the run with the Eddington limited feedback in blue. One thing to note, however, is that we do not allow the black hole to accrete right away at super Eddington, as it would basically trigger an immediate feedback response so powerful that it would sterilize the entire environment of the black hole, and therefore the accretion would basically stop almost right away because it's so powerful. So that's why we wait a little bit more than 40 million years in an Eddington limited regime before actually switching on super Eddington. And the difference is quite notable. The black hole that was able to grow at an Eddington limited pace actually grows quite close to the limit, despite the supposedly strong feedback it produces. However, the black hole with super Eddington feedback, well, doesn't grow much at all. In fact, it only gained like 10% of the mass it had back when we allowed for super Eddington accretion here. So the feedback seems to be quite detrimental to the black hole's growth. And we can actually see this when we have a look at this at the Eddington fraction. So on the left-hand side in this plot, in the main plot at least, you see averages and medians and quartiles for both the super Eddington and Eddington limited runs. And what is clear here is that the black hole that is able to grow above the limit, well, actually spends on average most of its time below this limit. And if we have a look at this at each fine time step, you see here in the inset the evolution of this Eddington fraction. And clearly there are some super Eddington episodes which are pointed by the arrows, but they all have a common trait. Mostly they are not very numerous, that's the first thing to see. But they also lead to a sharp drop down to very sub-Eddington accretion rates. So basically, that's the main reason why the black holes don't tend to grow, at least in this simulation, above the limit quite consistently. We also see that the super Eddington episodes seem to be kind of frequent because the intervals between like 2 episodes can vary from like 1 million year down to 40,000 years throughout the entirety of the simulation. So they happen on a sort of regular basis. On the right-hand side, in the second plot, you have the distribution of the total mass that has been gained in the super Eddington simulation, so the orange one, both in the radio mode, so when the Eddington fraction is below 1%, the quasar mode, and the super Eddington mode. And here you have the duty cycle, basically here. And what you see is that the black hole was only able to be above the limit less than 1% of the time, okay? However, this little amount of time that's spent above the limit actually contributed quite significantly to the total black hole mass. It contributed to about 20% of the mass gained by the black hole. So whilst it's true that the quasar mode actually allowed for most of the growth, it's important to notice and understand that the super Eddington regime can indeed gain a significant amount of mass, but there also needs to be a lot of super Eddington events, so a high duty cycle, to actually be visible in the black hole growth. Then we also had a look at the evolution of the feedback power and feedback luminosity to understand how it behaves, like how it triggers so many sub-Eddington episodes. So here you see the same color scheme as before in the previous plot. And in the Eddington limited case, we see that the power keeps on increasing, the feedback power, which translates basically the growth constantly at the limit up until it reaches in this region a few 10 to the 44 ergs per second, where the black hole became massive enough to reach self-regulation. And in the super Eddington case, once again, we see these spikes that are shown by the arrows. So that shows that the super Eddington regime actually releases like a lot more power, which heats up the environment quite quickly and therefore reduces the accretion rate overall. So when we take a look at the bigger picture here, we see that the AGN feedback injection is actually lower in the super Eddington regime than in the Eddington one on average, because there's a balance between the shorter-lived and higher power super Eddington episodes, which actually only last for one time step, and the much longer-lived sub-Eddington feedback episodes. And if we combine these results with the Eddington fraction evolution that we've just seen before, it captures the fact that the super Eddington regime actually requires less AGN feedback to reach self-regulation. So now, how about the evolution of the gas properties? We've seen that the super Eddington has a strong impact, but what about the gas on parsec scales, where basically the feedback is actually injected? So here I have a look at the evolution of the temperature, the average temperature and average density over 50 parsec, which is roughly the region that we inject the feedback. And clearly, as soon as super Eddington was allowed, which was right at this point, a huge jump, instantaneous jump in temperature happened, from reaching from a few 100 Kelvin to almost a few 10 to the 9 Kelvin. So this jump was caused by the very high power feedback event that was happening. It also pushed a lot of gas, as you will be able to see in just a minute, outside of the galaxy. It ejected quite a lot of gas as the density dropped several orders of magnitude, but the drop is not as sharp and strong as the big jump in temperature. It takes, of course, a little bit of time for the shock to propagate. That's why the decrease is not as sharp. We also see later on several super Eddington episodes which lead to not so much disruption of the density. However, we still see these very high jumps of temperature, which are, once again, the main reason why the accretion rate is reduced. And if we actually have a look at this in some movies, because it's nice, we have a face-on view and an edge-on view of the temperature and the evolution of the density over this same time scale. And we see that the feedback, which is mostly kinetic in this case, actually ejects a lot of gas away from the disk.
3 minutes, Warren.
Thank you. The reason why the reason why we see actually so many super Eddington episodes is that the gas gets replenished quite quickly, as you can see actually in the face-on view. The cold and dense gas actually swirls in, which is actually not impacted at all by the AGN feedback, because this outflow is perpendicular to the galactic plane. So overall, we've seen that the super Eddington feedback actually left some traces of its activity. And when low temperature gas is actually available for accretion, a new super Eddington event actually arises. It heats up instantaneously the gas and gives a lot of momentum to its surroundings, okay, and ejects some gas away from the galaxy. However, we've also seen that it does not have a long-lasting effect on the vicinity of the black hole, because the gas got replenished quite quickly, and therefore it triggered more super Eddington episodes. Finally, I'd like to just have a little mention of another study that we've done, which was done because super Eddington sources don't always have a strong kinetic bipolar outflow, as we have seen in the movie. Some surveys, such as the CMBH ones, actually find super Eddington sources which are radio quiet. And doing a similar analysis of this, we found that doing a thermal only run, so one without any jets, we found that the black hole was actually able to grow above the limit with feedback quite well. And this was actually well translated and well understood, because the actual frequency at which the black hole was going above Eddington, so the duty cycle, was increased by a factor of 10 in comparison to the previous run in orange. And despite really seeing the same amount of the same power in the feedback, it did not disrupt. I forgot to put the movie on. It did not disrupt the environment as much. So as you can see here, you have this feedback event that happens right here, but it doesn't disrupt it doesn't decrease the density. So the gas is still available for accretion even after some super Eddington feedback events happened. So I think I'm right on time. So I'm going to leave you with the conclusion, and I thank you, the organizers, for this RAM talk. And please, everyone, if you have any questions, feel free to ask them.
Thank you, Warren. Very interesting talk and bang on time. So I'm putting up my list and I'm waiting for questions. Please raise your hand with the reaction if you have a question. And as Yoki said, great, no way. I have a question. We have a question. Perfect. Unmute yourself, please. We can't hear you.
Okay. Yeah, a question. You mentioned the effect of resolution in your space exploration. What is the resolution of your simulation, and what is the size of the box?
Yeah. So the halo is actually 50 kiloparsec. Okay, the galaxy was about 1 kiloparsec, and the injection region is about 50 parsec, and the resolution is 13 parsec. We are currently studying the effect of the resolution by going from a level of 25 parsec and a resolution of 6 parsec. So that's still work that is undergoing, but we find so far that the black hole in the lower resolution simulation is able to grow actually to the same mass. Is able to reach the same mass, but doesn't grow too much either above the Eddington limit.
Thank you. Pierre.
Hi, yes, thanks for the great talk. I was wondering, maybe you're not at that level of analysis yet, but are the galaxies you are producing already compatible with say anything like the luminosity function of AGNs at the epochs that you're looking at, or does that provide any guidance into how likely or how unlikely the super Eddington mechanism can be?
So I think so. Thank you for the question. So the galaxies the one galaxy that I produce, because this is an idealized setup, is extremely compact. And once again, we are in an idealized setup, so that's not the best environment, that's not the, let's say, the most since we're not in a cosmological simulation, we cannot reproduce what we actually see at a very high redshift at the moment with this idealized setup. What we wanted to have was basically just a setup which was able to allow us for consistent super Eddington accretion for a certain period of time. And in regards to the luminosity function, as you just mentioned, I will have a look into it because I haven't analyzed this. But I think that we would have a good idea on this if I do a cosmological run. I believe that we've reached the a good enough resolution in a cosmological context to actually have some possibilities of super Eddington accretion. Yes.
Thanks.
Okay, can I ask, I'll ask one last question. Is there RT in your simulation?
No, so this
okay, that's okay. But
okay.
What's the physics behind the photon trapping? I was just wondering, is there any hope of doing simulations where you can follow that?
So these simulations, well, on Ramses, since I'm reaching resolutions just down to the parsec scales, okay, I can't really do things that include photon trapping because the photon trapping happens on like, let's say about 1,000 Schwarzschild radius, maybe even a little bit more. And these studies that you can refer to this here are the people who have done this work regarding the photon trapping. So basically, yeah, photons get trapped, can't radiate away, and I'm using their results to actually get an idea on the accretion rate.
Thank you very much. Okay, so can I invite Seonwoo to set up her talk?
Okay. Okay, so can you see my screen?
Yes, perfect.
Okay. Thank
So
you.
now we have Seonwoo Kim, who will talk to us about the mass segregation of galaxies in clusters. Thank you.
Okay, good morning and good afternoon, everyone. My name is Seonwoo Kim. I've earned my master's degree at Yonsei University under Professor Seong Lee, and will be going to ECOR for a PhD. Today, I will be presenting about the mass segregation of galaxies in clusters, and I used observations and a set of simulations, WISEX. This work was published in the Astrophysical Journal last year in December. So we know well that galaxies are influenced by their surroundings. In clusters, the combination of various environmental mechanisms results in the well-known dichotomy where galaxies in the inner volume of the clusters tend to be ellipticals, redder, and have low star formation rate. Other than that, galaxy and halo mass is also expected to be segregated, with the more massive ones in the inner volume. So the schematic diagram on the right illustrates this. The darker colors represent the more massive galaxies. This mass segregation is expected to happen because of dynamical friction. So dynamical friction is basically a sort of friction where the lighter background particles drag the massive orbiting object that's nearby backward. Dynamical friction transfers the orbital energy of the satellite galaxies to the gas and particles of the host halo, and this causes the satellites to lose their energy and make them migrate to the center of the cluster. So this dynamical friction formula gives the merging timescale, which is shorter for the more massive galaxies. And so therefore, the massive galaxies reach the cluster center faster than the less massive ones, and we expect the mass segregation to happen. However, there's no general agreement on whether mass segregation is actually visible or not. There are many examples in the literature, but here I brought two. In Contini and Kang, they used semi-analytic models and found mass segregation in groups and clusters. On the other hand, von der Linden found no mass segregation while using SDSS clusters. In this work, we used a set of zoom-in hydrodynamic simulations and observations also to find out whether mass segregation in clusters are seen or not. We first used Y6, which is a set of cosmological zoom-in simulation performed with Ramses. Baryon physics recipe is based on the Horizon Adrianne simulation, including Adrianne feedback and supernovae. WMAP7 cosmology is used, and the mass and spatial resolution is as shown here. So the simulation, the dark matter only simulation was first run within this cubic volume of 200 co-moving megaparsec. And then 16 dense regions were chosen as clusters. And then the selected 16 volumes out to 3 video radii was backtraced until their initial condition. And finally, the hydro zoom-in simulation was conducted. We then used ChIDisk, which targets 14 able clusters. Photometry was first done in the UGR band using IMAX on Magellan, MegaCam on CFHT. And then follow-up spectroscopy was done using the IMAX on Magellan, WCCD on DuPont, and Hydra on Wind telescope. Using the redshift information from the literature and the formula from Bell 2003, the stellar mass of the galaxies were derived, and it resulted in 1409 cluster galaxies. So when mass segregation is visualized in the literature, cluster-centric distance is used as the x-axis, and the log of mean stellar mass is mainly used as the y-axis. For a fair comparison of the observed and the simulated data, we made 100 random projections to Y6 in order to derive the 2D cluster-centric distance. The Y values are derived by applying bootstrapping to the mean mass of galaxies, which are included in each radial bin of different clusters. The black line is for Y6, and magenta is from the ChIDisk data. And the shades represent the 1 sigma values around the mean. And as you can see pretty clearly, that there is no mass segregation seen for both sets of data. But one thing we have to consider is that the distribution of galaxy mass depends on the cluster mass. So we use the fractional analysis to properly normalize the mass functions of galaxies in each clusters. We first defined the massive galaxies as the galaxies that are more massive than top n% of the galaxies in each cluster. And then we bin the galaxies into concentric shells like this, and like the figure on this right, and measure the number of massive and less massive galaxies. And then we finally derived the fraction by dividing the number of massive galaxies by the total number of galaxies included in each concentric shells. We repeated this process for all clusters, and the mean of fractions in each distance bin of all clusters is taken as the final value. And we used 50% to illustrate, and this was the result. The error bars and the shaded region represent the 1 sigma scatter. And for Y6, which is shown as black line, we can see clear mass segregation. And for ChIDisk, shown in magenta, we see a marginal trend. But will it be safe to use just arbitrary percentage? To check this consistency, we drew the same plot, just like this one, using the percentage range from the top 5% to 50%. And then these plots were fitted linearly like this, and the slopes for different percentages were derived. The x-axis on the figure on the right is the top percentage that was used, and the y-axis is the fitted slope from the previous plot. So the Y value below 0 indicates that there is mass segregation. And if we see the result, we can see a robust mass segregation trend for Y6, and this is marginally visible for chi disk. So we concluded that there's at least a marginal degree of mass segregation, and we decided to delve deeper into the physical explanation of why mass segregation is visible or not by using the Y6 data. Since we now only use Y6 to go back in time, the mass cut can be lowered to 10 to the 9 solar mass if we consider the mass function. We will now look at the mass segregation trend of individual cluster. The x-axis on the figure on the right is the mass of the Y6 clusters, and the y-axis is the slope of the scatter points in the left figure, which is stellar mass versus cluster-centric distance. So having a negative y value on the right figure on the right means that there is mass segregation. So the error bars indicate 1 sigma, and the red line is the linear fitting of the black dots from individual cluster. And we found a negative cluster mass dependence on mass segregation. But why is the degree of mass segregation different for different clusters? We know that dynamical friction makes mass segregation if it was visible. But galaxy mass is stripped via tidal stripping, which dilutes the mass segregation trend. So we think the degree of mass segregation is a result of the tug of war between dynamical friction and tidal stripping. The less massive clusters show mass segregation because they lose less mass. And to test our theory, we divided the Y6 galaxies into 2 groups, the less massive ones and the massive ones. To quantify the degree of mass stripping, we first defined the infall time of galaxies as the last time that they cross 1.5 virial radius from the cluster center. And then we compared them with the current mass of galaxies with their infall mass. The magenta in this figure represents those from the more massive galaxy clusters, and the cyan is for the less massive ones. The bases of the arrows are the mean galaxy mass at the time of infall, and the arrow tips are from the mean galaxy mass at the current epoch. So infall to current epoch. So if an arrow goes down like this, it means that the galaxies lost mass. As we see that the galaxies in the inner volume of the more massive clusters lost much more mass than that of the less massive ones. Then why did the galaxies in massive clusters lose more mass? We assume that one of the reasons for this is related to the time galaxies spent in the cluster. This figure shows the kernel density estimation of redshift at infall for the 2 halo mass groups shown in magenta and cyan. The bandwidth is determined by Silverman's rule of thumb. And although the scatter does overlap, more massive clusters shown in magenta have consistently higher values of Z infall in the inner volume. And also, the arrows shown here are upper limits, so we can say that massive clusters have marginally higher Z infall values in the inner volume than the less massive ones. Now, we can say that since the galaxies in the less massive clusters spend less time in the cluster, they lost less mass, and thus they show mass segregation. So, and then we cross-check our scenario with the dark matter halos, because the dynamical evolution of halos precedes that of the galaxies.
3 minutes.
We match the, okay, thank you. We match the galaxies and halos by using the linking length in 6 dimensions. The y-axis of this figure shows the ratio of the current halo mass compared to that at the time of infall. So having a smaller y means that the halos lost more mass. The first panel shows the ratio of the 2 halo mass groups, shown in magenta and cyan, And the second panel here shows the same, only for the less massive ones, shown in cyan. And they are divided into 3 Z infall bins. The dashed line at the bottom is for the recent infaller. The dashed line at the bottom are subhalos with higher Z infall, and the dotted line at the top is for recent infallers. And the error bars here show the typical scatter. We see in panel A that the subhalos in the inner volume lost more mass than that of the outskirts. And in panel B, the subhalos that spend more time in the cluster lost more mass as expected from the previous results. So here's the summary of my work. We use WISE-X and observations to examine the existence of mass segregation. If one asked me, does mass segregation exist? Then I would probably say it depends on the cluster, because less massive clusters show mass segregation. This happens because tidal stripping dilutes the mass segregation trend, and in less massive clusters, the galaxies in the central volume generally spend less time in the clusters, so they lost less mass. If we consider this, the disagreement on mass segregation can now be reconciled. You can read more about this work published in the APJ journal. Thank you so much for your time.
Wonderful. Thank you very much, Seonwoo. Questions? Are there questions? Please raise your hand. I'll give you a question while everybody else is thinking. So you looked at the mass segregation. Did you see any segregation by morphology?
To look at their morphology, I probably have to look at the particle distribution in the simulation. But I felt that the resolution should have been a little bit more better for me to divide them properly.
Understood. Okay, Patrick. Patrick has a question for you.
Yeah, hello, nice talk. Yeah, I was wondering whether numerical convergence is achieved in your simulations. I mean, if you essentially, I mean, repeat the rounds with more resolution, do you find the same result for the for this segregation?
So, if I understood correctly, were you asking about if the results would be the same if the simulation was run with different resolutions?
Yes.
Honestly, I only had one resolution within 3 view radii, so I cannot give you the perfect answer, but my understanding is that because we have pretty good resolution in the radius of the cluster, then I feel like the result would be pretty similar if we use different resolutions.
Yeah. Okay. Just a quick suggestion. Maybe you degrade the resolution by a factor of 2 because it's quick, and then you can see whether your results are the same.
Okay. I think that would be a good. That would be fun to look at. Thank you for your comment.
Sukhyun, unmute yourself, please. We can't hear you. No.
I can't hear you.
Maybe it's a sign that the supervisor can't ask a question.
Can you hear me?
Yes, okay.
Okay. I had a answer to your question, Adrianne, regarding whether there is a radial trend of galaxy morphology inside clusters. I I remember Suri, my former student, who used Chi-disk observational data, the same data Seonwoo used, and then she indeed sees a very strong radial segregation of morphology.
Okay, thank you.
I forgot to mention about the observations. Thank you.
Perfect. Anybody have one last quick question before we ask Ricarda to set up? No last quick question, but you could still, of course, discuss with Seonwoo in Wonder Me World or on Slack. So let's move on to Ricarda, please. So Ricarda,
Thank you.
Invite you to set up.
Hello everyone, can you hear me fine and see the screen?
Yes.
Can you see my cursor just so I know if it's worth pointing or not?
Move it around. Yes, we can see it.
Okay, brilliant. Lovely to see, at least virtually see you all. I'm Ricarda Beckmann. I'm currently based at the Institute for Cosmology in Cambridge, but most of the work I want to present you today was done while I was in Paris for the last few years at the IAP, working with Johan Dubois, Pierre Guillard, Philippe Salomé, and the rest of the Lyrics collaboration. And I want to show you some work that is hopefully very close to being submitted on cosmic rays and the multi-phase gas in galaxy clusters. So we're sticking with the theme here. And what I particularly am interested in is understanding how cosmic rays influence the cooling flow problem in massive galaxy clusters. So the cooling flow problem is very nicely summarized by this plot on the left-hand side here, where if you, for a wide variety of galaxy clusters, if you study the cooling rate you'd expect by X-ray observations from the hot gas. So if you work out how much energy they're losing and how much mass you should, cold gas mass you should be forming in the cluster per year. And if you compare that to the star formation rate, you can see that the trend is not at all linear. In fact, most galaxy clusters have considerably more cooling in the hot phase than they have star formation at the cold phase. I've had a very good analogy for this. This is a little bit like you imagine you've got 100 skiers starting at the top of a slope, but only 5 arrive at the bottom. So the question is sort of what happens in the middle, right? Why does a lot of the gas that is cooling at the hot end never make it to the cold phase? And how does it seem like galaxy clusters actually have very limited star formation rates and maintain a very steady state for very long periods of time rather than having these rapid runaway cooling flows that you would otherwise expect? So that's sort of one side of the problem and it's understanding how the gas evolves across the multi-phase range and how the cooling is offset in some of these massive galaxy clusters. The other one is to do a little bit more with what the multi-phase gas looks like in the process. So on the right-hand side here, we have a bunch of observational images from different galaxy clusters, and it's showing the sort of warm gas in the cluster center. And you can see that the gas is very present and it has a very particular morphology. So you can see that we have these nebula centered on the galaxy cluster. They're very large, so the brightest cluster galaxy will be in the center of this object, but these nebula extend far beyond the central galaxy. And they tend to have these very filamentary, stretched out morphologies. So the question that we are also trying to answer is why does the sort of warm gas, or the one that is between the hot and the star forming phase, have this particular structure in galaxy clusters, and what role does that structure play in maintaining the cluster cooling flow? So, the open questions, just to briefly summarize, is what reheats cluster gas and prevents it from reaching the star forming phase, what drives the particular morphology of gas that does cool and condense, and what physics are vital to maintain the self-regulation in galaxy clusters. So a lot of work has been done on this using isolated galaxy cluster simulations, because they make a very good test case to sort of compare and contrast various approaches to see how individual pieces of physics change. So that's something I did in my last paper published in 2019, where I used hydrodynamical simulations of an isolated galaxy cluster to particularly study how the gas morphology changes under the influence of an AGN jet. So what we typically do is we take a galaxy cluster, we set it up initially in hydrostatic equilibrium, we place a massive, supermassive black hole in the center, and then you turn on cooling and you turn on feedback and accretion from the AGN. So as the gas starts cooling onto the cluster center, it feeds the black hole, which then releases a jet, which then returns energy to the intracluster medium. And thereby you've got this link between the cluster cooling and the reheating from the AGN. And what I did in this work here is I particularly try, and it's not just me who's done this, there's been a very strong body of work showing that AGN are probably one of the core processes that drive, this cluster heating. So you can very closely link the cluster cooling flows that develop to this AGN. The more cooling flows you got, the more AGN energy you get. So it very nicely sort of has a feedback, self-regulating feedback mechanism where the cluster can, I don't want to say fine tune, but basically keep itself in a rough thermal balance over long periods of time. So in this work here in particular, I studied a lot how the cold gas mass relates to the AGN activity. So if we look at the plot we got the cold gas mass over time in blue, that's this line here. And you can see very nicely the very strong link with the AGN luminosity, which is this black line here. And you can see they're very closely linked. And you can also see that over at least the gigi of evolution I studied here, the cluster doesn't, after an initial phase is very well balanced. We have roughly the same gas mass across long periods of time. We have a AGN luminosity in a fairly constant band. And we don't see a sort of runaway effect at late time. So we don't see a complete shutting off of cold gas formation, but rather we see a relatively steady evolution. So that's in the sort of global picture. But if you look at the morphology of the gas in the cluster center, we see a lot of evolution. It can at times be very filamentary, like we saw in some of the observations, or at other times it can become, at least in the simulations we had, it became very, very clumpy. We saw little disks and then back to more filamentary structure. So despite the fact that we have, the cluster in general is fairly well settled, the morphology of the gas in the cluster center changed on 100, 200 megayear timescales quite dramatically. And a lot of that was to do with the direct interaction with the AGN, where exactly the energy gets injected, which direction the jet is in, because that will determine where these pockets of thermal instability form, where gas spontaneously cools from the hot phase to the cold phase and sort of appears in this intermediate range where we are studying it here. So that was sort of the work I did in 2019. And then, you go to conferences and people ask you questions. And it usually goes along the lines of, what about magnetic fields, cosmic rays, or dust? We've had the dust covered, so we already had the dust in the simulations. But today I want to talk about basically, what about magnetic fields and cosmic rays in this environment? And we think they're both, clusters are magnetized, they have very weak magnetic fields, but they're certainly there, both in and around the galaxy. We know very little about their morphology, so we know very little about their structure. So there's a lot of sort of research left to be done trying to understand how we think magnetic fields are structured in galaxy clusters. But there's certainly a hint that they might play an important role in particularly the structure of this extended filamentary gas. There's field lines, if they have long coherence length, would make a perfect sort of structure to explain why the gas in observations is preferentially very long and extended, rather these sort of more clumpy structures that we get in the non-magnetized simulations that I've showed you here. And cosmic rays could provide sort of two key pieces of the cooling flow puzzle. So apart from the overall question, if they exist, we need to understand what influence they have. They seem like a very promising idea that might make a big difference in these cluster environments. And there's two reasons for that. One is that the observed nebulae that we see in the galaxy clusters are warmer than you would naively expect from their cooling times. So they have very short cooling times, which means they should be very cold and star forming, but rather they tend to be maintained at a fairly warm, intermediate, 10 to the 4, 10 to the 5 Kelvin gas. And the question is, how do they maintain that over long periods of time? And one idea is that if they contain cosmic rays, the cosmic rays act as a non-thermal source of energy. So essentially it's like having a secondary energy reservoir that doesn't cool in the same way that gas does. So if you could slowly transfer energy from the cosmic rays into the gas, you could basically have like a steady heating source that offsets some of the radiative cooling that would lead to runaway cluster cooling. And the same applies on a larger cluster scale. So if you had a lot of cosmic rays in the cluster center, you might very well end up in a situation where the cosmic rays can provide a steady volume filling, large scale source of energy that can offset some of the cluster cooling. But whether this can happen depends very strongly on the conditions. It depends very strongly on where the cosmic rays end up. And it also depends on the observational constraints. So there's very stringent upper observational constraints on how many cosmic rays we can have in galaxy clusters. So the question is whether what remains below that constraint can make a meaningful difference to cluster cooling flows over long periods of time. So this is one of the things we tested in these simulations. We essentially replaced, we took the same simulations I had before, but we added magnetic fields and we added cosmic rays, which are injected in one of two ways. Some of them, essentially we already have classic energy injections in these simulations through supernova or through the AGN jet. So these are the two ways we directly inject energy as the simulation runs. So in this case, we in both cases converted a fraction of that energy to cosmic rays. Now in massive galaxy clusters, the supernova are not very important. I'm going to focus on the cosmic rays injected by the AGN jet because the vast majority of the energy in a galaxy cluster is injected by the AGN, not by a supernovae. So what we did is we maintained the link between the black hole accretion rate and the AGN luminosity. So if you look at the formula here, we have a black hole accretion rate calculated based on the local gas supply. We use Bondi-Hoyle-Littleton, but it's not particularly important. It's essentially to do with the conditions right in the cluster center. And then a fraction of that gets converted into AGN luminosity. In particular, usually, this ER, this epsilon I is the efficiency. Ours is based on the spin of the black hole, but a typical value would be around 15% or so. And then we take this AGN luminosity, which sort of represents our total energy budget for the AGN, and we split that into two channels. Now, classically, you would probably put most of that in kinetic energy. So you would accelerate the gas above and below the black hole to drive large-scale jets. But we maintain that, we want jets, we see these large-scale extended jet structures in galaxy clusters. So jets are clearly an important part of the equation. But rather than putting it all into kinetic energy, we put a fraction into cosmic ray energy instead. So we essentially injected cosmic rays at the jet base, as well as kinetic energy, and then they get transported with the jet as the jet expands to larger scales. The flip side of that is, though, that less energy is left for the kinetic channel, and this is going to become important later. So we essentially tested three values. We tested a purely magnetized case with no cosmic rays. So we set this value of FCR to 0, so we've got an entirely kinetic jet. We tested a case where we put 10% into cosmic rays, and we tested a case where we put 90% into cosmic rays. And I've got some images for all three simulations here, 1 gigayears, 2 gigayears, 3 gigayears. And you can already see that it makes a big difference to the morphology of the gas in the cluster center. Right, in the MHD case, we build up this incredibly massive, very dense central blob right around the AGN, which is marked by this black cross here, as well as some larger scale filamentary structures. With only a small fraction of cosmic rays, so 10% of the total AGN energy, we have a considerably less massive central structure and a much more filamentary morphology. Whereas with very strong cosmic ray feedback, we get very large, very extended, much more diffuse nebulae that cover much larger cluster scales. You can see, we're going out to almost 50 kiloparsec here, versus these tend to be much more centralized. And this difference becomes particularly obvious if you look at the phase plots. So what we've got here is we've got 3 snapshots from all 3 simulations. I picked one halfway through the simulations, about 1.5 gigayears. And above it, we got phase plots for that same simulation. So shown here is is a stacked sample that shows temperature versus density for all the gas in the simulation. And you can see that there's a certain number of phases emerge. So for example, if you focus on the MHD simulation only on the left here, we got an obvious hot phase. There's a lot of gas in the hot phase, which is the intracluster medium. Then we got very little gas in this intermediate temperature range here, because gas here cools very, very rapidly. So gas essentially cools from hot to sort of a few times 10 to the 6 Kelvin, then it cools extremely rapidly to 10 to the 4 Kelvin. So you find very little gas in this phase at any point, one point in time. And then it continues to cool across along roughly this orange line here. As it becomes colder and denser, it collapses into denser structures. And as a result, the simulation, if you stack across all periods of time, which is this dotted blue line at the top here, we can see the distribution of densities has this very dense tail. So there's a certain, a significant amount of very dense cold gas that forms in the simulation over long periods of time. The case with only a small fraction of cosmic rays, interestingly, looks very similar to the MHD only case. So we still have this cooling at the hot phase, rapid drop off in the intermediate phases, but maybe a hint of a little bit more warm gas building up in this area here. And then again, the secondary sort of cooling at the low densities.
3 minutes, Ricarda.
Okay, yeah. But we find much less of, we find the dense phase, but we find much less of this very cold phase. So the dense phase that exists in this case is dense but slightly warmer. But the picture changes almost completely if you go to the strong cosmic ray case, in which case a lot of gas gets trapped in this warm phase. In fact, we see very little dense gas at all if you compare this, and instead see this diffuse warm phase developing here, which isn't present at all in the other simulations if you compare where the dotted lines are. So rather than cooling isobarically, so basically along these orange lines, we say gas starts cooling isochorically, which is at a constant density. So basically gas cools, but it doesn't collapse. And that's because the gas is supported by the cosmic ray and by the cosmic ray pressure, which changes its overall gas phase. And this has an important impact on the long-term evolution of the galaxy cluster. So if you look at the overall time evolution of warm and cold gas, so gas below 10 to the 6 Kelvin over long periods of time, we can see that the MHD case only, as we already saw in the images, we build up huge amounts of gas. So these yellow lines spike very, very high, 10 to the 10, almost 10 to the 11 solar masses in gas. And that's a sign of a runaway cooling flow. The cluster is overwhelmed by condensed gas, and the AGN struggles to sort of break that up, and in this case actually loses the battle at the end. It's unlikely to recover. Whereas adding even a small fraction of cosmic rays helps maintain that. So you stop with this runaway buildup of cold gas, and the results are much more steady, like we saw before in the hydro case, which is shown here in red. But how it happens is a little different. In the weak cosmic ray case, most of that gas is in cold gas, so below than 10 to the 4 Kelvin, whereas if strong cosmic rays, in fact, most of the gas is in the warm phase. So we actually have a lot of gas, over 10 to the 9 Kelvin for long, long periods of time maintained in these warm gas phases. And the reason for that is because with the two different simulations, the distributions are quite different. So because in the weak case, we have a strong kinetic jet, so a lot of kinetic energy, the jet remains its general, structure and carries the cosmic rays with it, maintaining them almost entirely within and around the jet cone, as you can see in this left image here. Whereas if you have a lot of cosmic rays, you have very little kinetic energy, so the jet becomes very weak. And because it has a strong nebula as well, it interacts with the nebula. So as a result, the cosmic rays, as well as there being more of them, are distributed much more isotropically in the cluster center. So you basically end up with a core. The entire core of the galaxy cluster is dominated by cosmic rays. And you can also see that here, the core stretches to almost 40, 50 kiloparsecs over time and sort of settles into a more or less converged case here. So you only get a very small core in the weak case. When we compared it to observations, we found that the strong cosmic ray injection, as well as not looking less like the images, in fact, also vastly exceeded the gamma ray constraint. So if you look, this is an observational constraint here on the black line. Purple is the strong case, and you can see we're vastly above it, versus in the weak case, we're much more in agreement. Now, take that with a pinch of salt. This is not the same object. It's only one example, and so on. But the general takeaway is that with very strong cosmic rays, you can have a huge influence in galaxy cluster cooling flows. But it looks like at the moment, at least, we're overshooting it. We're overdoing it in comparison to the observational constraint. Whereas a small fraction of cosmic rays injected into the jet helps maintain the cluster balance and is in agreement with the observation. So that might be the sweet spot where we think cosmic rays might have, might play a role in cluster cooling flows, but not, dominate them as they could do if there was a lot more of them, but probably don't because of the observational constraints. And I'll leave you with my conclusions. Thank you very much for listening.
Thank you, Ricarda. That was really great. Questions for Ricarda? Please raise your hand. So while we're waiting, I'll ask a quick question. You showed a plot of the mass, and the MHD run was, I'm wondering why the magnetic fields suppress the mass more than in the hydro run. How does that physical process work?
My bad. Let's go back to
towards the end of your talk.
Was it this one?
Yeah, the top plot.
Yeah, exactly. So this is one of the things that puzzled me as well, right? I expected the MHD one to look roughly like the hydro run, so for the red line to be very similar, but actually we found that you get a lot more cooling if you add magnetic fields, you get more thermal instability in galaxy clusters. I'm not 100% sure whether this process is very well understood. There are certainly papers out there that have shown this using isolated, cooling boxes where you put gas in a box and you study how thermal instabilities develop under, a certain amount of turbulence. And they also found that it does seem to be the case that the presence of magnetic field actually favors thermal instability. So you get more of these pockets of cold gas condensing, which basically means in our case, the AGN has to work harder to offset it. And it seems to really struggle to make up for that difference completely. So funnily enough, the hydro runs are more easily balanced than the pure MHD run. But then adding a small fraction of cosmic ray can offset that again, because that again helps to stabilize it a little bit and again changes, adds extra local pressure that offsets some of this thermal instability. So a little bit of cosmic rays kind of counteracts the magnetic fields and you're back to something that looks more like the hydro run, funnily enough.
Okay, I'm going to ask Wonky Lee to ask his question. Please unmute yourself.
Okay, yes, thank you for your great presentation. It was very interesting. I have a question on the first open questions. So you've changed the cosmic ray energy. So I was wondering, did it affect the morphology that you mentioned in the first slides, the morphology of the filamentary structures or number of fragments that we see in observations?
Yes, so this is a good question, and it's something I haven't analyzed in an awful lot of detail yet. So I've so far focused on the large-scale cooling flows. But if you look at the images, you can definitely see that there's certainly a difference, right? One of the reasons I'm a little wary of diving into too much detail into the morphology of the filaments here is because to be able to afford the cosmic rays and the magnetic fields, we had a somewhat lower resolution. And the filaments in the observations are extremely thin. So here the resolution of the simulation is bigger than the sort of average width of filaments in observation. So, we couldn't reproduce the exact morphology if we tried. But I think that the next interesting step would be to take, now that we think, maybe 10% of cosmic rays is a good fraction to study in galaxy clusters, to take one of those simulations and rather than have a whole set of simulations, do that one in a large amount of detail to go and look in, study exactly how the morphology of the central structures evolve over time. It's something I've been thinking about, but I haven't got around to. A very good question.
Thank you. Okay, one last quick question from Tayson, please.
So you might have thought about this already, but so have you had a chance to compute any observational signatures in terms of the warm gas? So here you're saying that you have increased the amount of warm gas, and I suppose that's the temperature where you can expect to see it's a little high, but still with lemon alpha, H alpha, and even the O3 emission lines. So you might have some, constraints from observations for that part.
Yeah, so that's another really good question and something I wanted to get back to, but haven't got around to. So part of the idea of the original LYRICS project was that it included observers, people who are specialists in modeling emission from different gas phases and, studying ionization states and the results and the simulations. And the idea was to bring them all together and, do very detailed sort of predictions for observations to compare. We haven't got there yet, but it was certainly something that would be very interesting because, like I said, the phases are quite different. So we would expect very different observational signatures from that. And that would certainly be something to look into. Thank you.
Okay, thanks.
Excellent. Okay, so we have to move on. Thank you, Ricarda. And Hugo is going to share his slides with us.
Yes. Okay. Up. Okay, you let me know and I...
Go ahead.
All right, thank you very much.
Go, and I will tell you in 3 minutes.
So am I the one with the bad connection or Adrian is the one with bad?
I think it's okay for you, Hugo. It's more Adrianne who's
all right.
The connection seems a bit bad. So go ahead.
Okay. Awesome. So thank you very much for organizing this conference. It's a shame we cannot meet for real, but I guess that's how it is. So for those who don't know me, I'm Hugo and I'm a postdoc in between the Dark Institute in Copenhagen and the University of Hong Kong. And today I want to talk about work that I've been doing for the past few years during my PhD, and I kept doing it during the postdoc, working on tidal dispersion events. So I will call that TDEs for the rest of this talk. So for those who don't know what TDEs are, let's assume that you have a black hole and a star with some property, and the star is at some distance from the black hole. And then if you want to know what are the forces that the star suffers, first you have self-gravity, which tends to maintain the star as a whole. And the expression of self-gravity is very simple, gm squared divided by the radius of the star square. But also if you, in your mind, if you cut the star in two, and you're wondering, okay, what is the force that this part of the star suffer, what you can very easily estimate it with Newton's law. And you have to understand that this part of the star, because it's slightly farther away from the black hole, the force that it suffers is slightly lower, right? And so this results in a tidal force, which tends to disrupt the star. So in the end, you have two forces, self-gravity, which tends to maintain the star as a whole, and tidal forces, which tend to disrupt the star. And you can wonder under which condition self-gravity is stronger than tidal force. And you end up with a very simple criteria, which is tidal forces are stronger than self-gravity if the radius is lower than some tidal radius, okay, which depends on the properties of the stars and the mass of the black hole. So if you understood what happens, it means that if the star penetrates the tidal radius, then it's disrupted. And you can see it very well on this very nice picture. You have your star at some point, and when the star penetrates the tidal radius, it's going to be disrupted. And you've had some very high-resolution simulations. Here's an example where people, they throw a star onto the black hole and they follow the formation, the disruption of the star and the formation of the accretion disk. When you have this kind of simulation, what you can do is to measure the mass accretion rate onto the black hole as a function of time. So here is an example from this Guillochon 2013 paper, and you see that he has run a set of simulation with different stars, with different masses, different density profiles from the star, and he measures the accretion rate onto the black hole. And if you know the accretion rate onto the black hole, then because the luminosity scales with the accretion rate and the magnitude scales with the log of the luminosity, you can infer the magnitude for a given black hole mass, stellar radius, etc. And you can go to observation and see if you have something which looks like that in the real sky. And this is an example of an object that we have found in this in a survey, and we're going to publish this paper in a while. But you clearly see that there is a resemblance between the magnitude of this object here and the theoretical curve here. And so the idea is that you can use the luminosity curve to obtain the properties of the black hole, the mass of the black hole, the radius of the star, the mass of the star, the density profile of the star, etc. And this is what you have done here. So you have the same data point for this object, okay, in different bands. And then we try to I mean, Charlotte, what she did is to pass some, to do some Monte Carlo simulation to try to see what is the best fitting model, and you can actually infer the properties of this object. So it's a few 10 to the 5 solar masses black hole, and the star which has been disrupted is about 1.3 solar masses. So you can see that with tidal disruption event, we can actually have information on supermassive black holes, and more importantly, we can have information on dormant supermassive black hole, because this black hole wasn't shining at the beginning. So now that you know what a TDE is, and you know that we have observed TDEs, some natural questions which arise: how many events, how many TDEs do we observe per year? And so you have this very nice paper from Short van Velzen a couple of years ago, where he basically shows the number of events per year per megaparsec cube, so per unit volume, as a function of the galaxy mass, okay? And so you have observations with the symbols. And this line here indicates the galaxy mass function, why you assume that you have one event every 10,000 years. And you can see that at least in the lower mass end of this plot, you have about one event every 10,000 years. So this is the number that we're going to keep in mind for the rest of the talk. The second question that you can wonder, now that you have more than one event, is the distribution of these events. So here you have some dependence with the galaxy mass, but very interestingly, if you plot here in the color, every dot is a galaxy of the SDSS. So here you have spiral galaxies, here you have ellipticals, and this marker indicates different TDs. And what is interesting is that in this corner here in the bottom right, you have about 1% of galaxies, but you see that you have a lot of squares, so you have a lot of TDs, and actually it's very surprising that you have 20% of the TDs in only 1% of the galaxies. And so this is a surprising observational fact, and also you may want to understand the dependence of the galaxy and the black hole mass. So with all these questions, we started to work on this with Marta when I was doing my PhD, and what I want to do is to summarize a few papers that I've worked on to try to address this question of TDs. So let's start with the rate of TDs in our universe. Can we understand how many events per year we observe in the sky? So as I recall, we should find about one event every 10,000 years. So what you can do is to say, okay, I'm going to set up a very simple numerical simulation, okay, and I'm going to count how many stars penetrate the tidal radius. So I draw a circle and I just measure how many stars enter the tidal radius, and I say, okay, these stars will be disrupted because the tidal forces are stronger than self-gravity of the star. But the issue is that if you remember the expression of the tidal radius, you find that the typical size for Milky Way-like black hole is about 10 to the minus 6 parsec. And as you all are all Ramses users, you know that this is completely impossible to resolve this scale in a galaxy simulation. So how can we do that realistically? Well, you should imagine that, you should understand that when you have a black hole which is surrounded by some density profile, in the end the rates should only depend on the density profile and the mass of the black hole. And actually there are people, starting with Lightman and Shapiro in '77, who have developed this loss conformalism, and I'm not going to get into the details of this, but knowing the density profile and the mass of the black hole, you can obtain how many events you have per year, okay? And so what I've done, and I'm not the first one who did that, but still use my figures, is I took some realistic galaxies, okay? So I went to observations and I used realistic density profiles. So here you have two examples of this density profile of two nearby galaxies, and you also know the black hole mass. And so you, on this density profile and knowing the black hole mass, you can apply the loss conformalism, and you can estimate the TDE rate. So I'm showing here the TDE rate as a function of the black hole mass. What I just want to show with this plot is that we can understand that typically you have 10 to the minus 5, 10 to the minus 4 events per year around supermassive black holes. So this is just to kind of justify that the loss conformalism is adapted to, allows to recover this TDE rate that we find in observations. So now I want to understand the second part, the second question that I showed you earlier. Can we understand why we have an overrepresentation of TDs in post-starburst galaxies? And so what I'm going to use is a simulation of a galaxy merger, because when you have a galaxy merger, you trigger a starburst, and so you will have naturally a starburst. So this is what I'm saying here. So you can run a simulation of galaxy merger, and you, at each time step, you estimate the density profile. And because you know the mass of the black hole, you can again apply the loss conformalism and have the evolution of the TDE rate as a function of time. So this is what I did in the second paper. So here you have a stellar projection, and you see the density profile around each black hole as a function of time. You also have the mass of the black hole. And so you apply the exact same techniques that I didn't explain, but the loss conformalism on the density profile with the mass of the black hole, and you can estimate the TDE rate. And so this is what I've done here, and I'm showing in solid line on the left the TDE rate as a function of time, okay? On the right panel, you have the density at some radius, and this is its dash, and the color indicates the two black holes. And you see that at some point you have a starburst, okay? And immediately when you have the starburst, you have an enhancement of the TDE rate. So you naturally reproduce the rate enhancement in post-starburst galaxies. This enhancement of the rate is naturally due to the fact that you have more stars in the vicinity of the black hole. And interestingly, okay, in this situation, so I label black hole 1 as the most massive black hole and black hole 2 as the less massive black hole. And it happens that in this situation, the enhancement appears on the secondary black hole. I will come back on this later. So now I want to see how the TDE rate evolves in a mock universe, and basically I don't want to have only one single galaxy, which is what I had in in the previous simulation, I want to have a lot of galaxies to know around which black holes we can find some TDEs, what are the most likely galaxies, what are the properties of the galaxies, does this rate evolve with redshift, does these TDEs have an impact on the black hole growth, because you can imagine that when the star is disrupted, you form an accretion disk, and then the material that was forming the star is accreted by the black hole, so this should in principle contribute to the growth of black holes. So to do this, you want to do that on the fly. Okay, you want to run a cosmological simulation, and you want to apply the exact same techniques that I depicted before, but you want to do this on the fly during the simulation. So you cannot stop the simulation, measure the density profile, apply the loss conformalism, etc., and update the black hole mass, and restart the simulation. So you want to do that, I mean, automatically in a sense. And so this is the reason why I implemented basically tidal disruption events as a subgrid model for Ramses. Okay, so very similarly to you have accretion from gas, which we had for many years now. With my version of the code, you also have accretion from stars. So how does it work? So you have your black holes, it's surrounded by a lot of stellar particles. And basically what I'm going to assume is that the density profiles which surround the black hole is a power law. So to estimate the power law, I simply measure the enclosed mass of stars within 4dx and the enclosed mass of stars within 8dx, and then I assume it's a power law. Okay, so everything is... So if you have the enclosed mass of stars within this sphere and within this sphere, you can infer rho naught and r naught and gamma. Now that I have the mass of stars and that I have the mass of the black hole, I can use the result from Wang and Merritt, which is basically a result from the loss conformalism, but basically knowing the mass of the black hole, gamma, rho naught, and r naught, I can estimate the TD rate. And now that I know the TD rate, I can assume that all stars are solar-like. And so, yeah, so there is a m dot missing here, but basically I remove this gamma dt, so this is the number of stars which were removed due to TDs in the simulation. I add a fraction of these stars onto the black hole. I add a, yes, okay, for the 3 minutes. I put back some stars into the medium, and also, very importantly, there is a fraction of the mass contributes to feedback. So I've run a simulation, classic Ramses cosmological simulation. Here, a stellar projection, the dots are black holes, and you have a yellow circle when the TD rate is larger than 10 to the minus 5 event per year. So as you can see, you have a lot of black holes in these simulations. They wander, you have one in the center, but sometimes you have mergers. And what is interesting is that you have many black holes, okay, but the total TD rate is going to be the sum of the TD rate of all black holes. And one interesting point that you can see very well here is that sometimes you can have wandering black holes which have a high TD rate, which is in line with what I was showing in the previous simulation. So just the last slide here, I'm showing the mass of the galaxy and the mass of the black hole. That is to say that it is consistent with observation. And now we have not only the mass that is accreted from gas in blue, but also the mass that is accreted from stars, okay, through the TDs. So the first comment you have accreted about 10 to the 4 solar masses in 1 gigayear, so that is a rate of 10 to the minus 5 event per year, so consistent with observation in the local universe, but already at redshift 6. And one important result from this plot is that if you look at massive black holes, TDs are completely irrelevant. So if you do not have TDs and you study very massive black holes, it's fine, you are doing things correctly. But in the low mass end of the black hole mass function for low mass black hole, okay, you see that the accretion due to stars is similar to the accretion due to gas. And actually, if you look at the fraction of material, so this is the fraction of material, the fraction of mass due to stars divided by the total mass that is accreted by the black hole as a function of time, and you see that in the early phase of the black hole life, stellar accretion dominates the growth of black hole. Okay, so in conclusion, when you have a star which gets close to a black hole, you have a TDE. Okay, this is a very luminous event. We have observed about a dozen of them today, and that is a rate of about 1 event every 10,000 years. And it depends on the properties of the galaxies. if you use the loss conformalism, you can recover this typical rate for realistic galaxies. I applied this TD rate in ideal simulation to study the evolution of the TD rate, and I found that when you have a starburst, you naturally enhance the TD rate. And then finally, I presented a simple subgrid model to self-consistently take into account TDs in simulation. And I found that TDs are important in the early life of black holes, and you can have a high TD rate on off-centered black holes. Thank you very much for your attention. I hope I didn't overextend too much.
Thank you. Any questions for Hugo? Please raise your hand. Christophe.
Hello. Thank you for a great talk. I have a naive question. Maybe you answered it already, but and then I apologize. There's obviously the issue of resolution in the last part of your talk, because you're going to measure the profile on the scales of the grid of the simulation, whereas the process itself is happening on 10⁻⁶ parsec. So how sensitive is your result to this discrepancy in resolution?
Okay, so it's an excellent question. Okay, so I lied a bit when I said that the process, the typical important scale is about 10⁻⁶ parsec. So this is the tidal radius. So this is the radius at which star is disrupted. But if you're interested in how many stars will enter the tidal radius, what I'm showing here, so this is a plot from Stone 2016. What I'm showing here is the number of stars which enter the tidal radius as a function of the energy of the stars. Okay, and if you assume that everything is Keplerian, you have that the energy of the semi-major axis of the star is going to be gm divided by 2 epsilon, where epsilon is the energy of the star and m is the mass of the black hole. And you see that it peaks at about 1,000 km/s². But whatever, if you take a black hole mass which is 1 million solar masses, this is the typical semi-major axis of 2 parsec. Okay, so this is actually the scale that you want to resolve is actually 2 parsec, not 10⁻⁶ parsec. And you're right, we do not resolve this this scale, even 2 parsec, we do not resolve it in the simulation. So I haven't done the convergent study, but so you are right that we extrapolate inward the density profile. So the resolution is about 7 parsec in this situation, and we measure the density profile within 4 and 8 dx. So this is about 40 parsec and 80 parsec. So this is one caveat of the model.
One last question, Patrick. Oh, sorry, Christophe, please.
No, that's it.
Okay. Patrick, please.
Yeah, thank you for the nice talk. I understand you assume that you get 1 solar mass stars. Well, in reality, I guess you should have an IMF, and I guess the gravitational potential of the various objects is not the same. So I wonder whether the result may be influenced by having full IMF, and whether by any chance, the reverse, by observations, you could actually constrain the IMF if you were sensitive to the mass of the star.
Yeah, it's an interesting question. So actually, I assume, okay, so there are 2 parts to your question. If I can find the model again. Okay, so here I assume that if you have, say, 1 solar mass per year, which is onto the black hole, I assume that only 50% of this mass is accreted onto the black hole, and 50% goes back. The thing is that when the star arrives, it has a very high eccentricity, so an energy of 0, okay? And so you can assume that half of the mass is going to have a negative energy and is going to fall onto the black hole, and half of the mass is going to have a positive energy and is going to be ejected. So it's not exactly 1 solar mass which is actually accreted onto the black hole. To answer your question of the IMF, you can show analytically that when you change the IMF, you can rescale the TDE rate very simply with basically the root mean square of the stellar mass of the IMF and the mean stellar mass of the IMF. So I don't have the plot here, but basically it's case that RMS of the IMF divided by mean stellar mass of the IMF. So if I were to assume an IMF, I could simply rescale the TD rate that is measured for monochromatic stellar population. And the reason to this is because the way you're going to bring stars onto the black hole is through two-body interactions. And so you can imagine that if you are living in a population where all the stars have the same mass, the number of interactions that you're going to have is going to be different that if you are living with in a universe with some low star mass and high star mass. But it happens when you do the calculation that the diffusion coefficient, so which tells you how you're gonna move in this potential due to two-body interaction, these diffusion coefficients they do not depend on your mass. So if you have an IMF, you can very simply rescale the results.
The tidal radius, I guess, is not the same depending on the mass of the star.
Yes, it's an excellent point. So we are working on this. I cannot. Okay, I can show you a plot offline if you want that shows you that even if you consider that we have done that here in Hong Kong, the effect in the end is minor. So in the end, the total rate can be obtained simply analytically. I can share with you the plots if you're interested.
Okay, fantastic. So we've reached the end of our morning first session, and thank all the speakers for excellent talks. I don't know if everybody could figure out how to do their clap hand little symbol. It's really great. So we have a break now, coffee break till 11:10. Can the speakers for the next session stay and test whether their slides work? I think that would be really useful.
I'm going to keep the session open during the coffee break, so people don't have to go.